Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, John Shinja. Today, we'll study Chapter 2, Fundamentals of Automatic Control, Correction and Design of Automatic Control Systems. In mechatronic systems, automatic control technology is the core link for achieving precise control and efficient operation. Correction and design of automatic control systems is the key step in implementing this technology. Next, we will explore the methods for correcting and designing automatic control systems. 1. Analysis of control systems. In engineering, analysis of automatic control systems focuses on stability, steady-state performance, and dynamic performance, with an emphasis on the latter two. Mathematical models form the theoretical foundation of control systems. Higher-order systems are often approximated as lower-order systems. Focus is placed on time-domain analysis of first- and second-order systems, with some discussion on frequency domain and state space analysis. 1. Time-domain analysis. This refers to analyzing a system's stability, transient, and steady-state performance by observing the time-domain expressions and response curves of output under a given input. 2. System response. System performance analysis depends on system response, which is determined by the mathematical model, initial conditions, and input signal. A unit step function, RT, equals 1 is commonly used as input, and the corresponding response is called the unit step response. 3. Steps of time-domain analysis. 1. Derive the output image function from a system's transfer function and the given input. 2. Perform the inverse Laplace transform on the output image function to obtain the time-domain expression. 3. Determine the performance indices based on the response curve or relevant formulas. 4. First and second-order time-domain analysis and conclusions. Classification of second-order systems. Based on the value range of the damping ratio zeta, the step response of the system can be classified as follows. Critically damped, zeta equals 1. Overdamped, zeta is greater than 1. Undamped, zeta equals 0. Negatively damped, zeta is less than 0. And underdamped, 0 is less than zeta is less than 1. The system is stable under overdamped and underdamped conditions. Due to the superior control performance of underdamped systems, they are widely used in practice. Standard equation. 5. Stability analysis of systems. In engineering, stability is the primary condition for the proper functioning of a control system. Unstable systems cannot function. The necessary and sufficient condition for absolute stability of a system is determined by the signs of the characteristic roots of the characteristic equation. For first and second order systems, the roots are easy to calculate, while for higher order systems, root solving is more complex. The Ralph-Hurwitz algebraic criterion, or MATLAB programming, can be used to determine absolute stability. 2. Stability analysis and algebraic criteria. 1. Concept and conditions of stability. A system is stable if, after a disturbance causes deviation from its original state, it gradually returns to that state once the disturbance is removed. The condition for stability is that all roots of the characteristic equation lie in the left half of the S-plane. 2. Methods for determining stability, Ralph criterion, and other algebraic criteria. For the Ralph criterion, a necessary condition for stability is that all coefficients of the characteristic equation are positive. A sufficient condition is that the first column of the Ralph table, formed by the coefficients, is entirely positive. When applying the Ralph criterion to determine system stability, the specific steps are as follows. First, derive the system's characteristic equation. 2 key points must be noted. 1. The powers of S should be arranged in descending order. 2. All coefficients must be greater than 0. For example, the stability condition of a third-order system is that all coefficients are positive and A1 times A2 is greater than A0 times A3. Using the Ralph criterion, stability can be quickly determined without solving high-order equations, which is highly practical in engineering design. 3. Analysis of process control systems. 1. Second-order time domain analysis. 1. Unit step response of second-order systems. Different damping ratios affect the system's response and dynamic performance. In practical engineering, underdamped systems are most useful, and controller parameters are often designed accordingly. From a unit step response curve of a second-order system, it can be seen that for a given zeta, underdamped systems reach the steady-state value faster than critically damped systems, while overdamped systems respond slowly. Hence, most control systems are designed to be underdamped. 2. Dynamic performance indices of second-order systems. Rise time, TR. Time to first reach the steady-state value, indicating response speed. Overshoot, the percentage by which the peak exceeds the steady-state value, reflecting oscillation magnitude. Settling time, TS. Time to enter the plus or minus 2% steady-state error band, measuring stability. These indices are core criteria in system design. For example, precision machining equipment requires overshoot less than 5% and settling time less than 2 seconds. MATLAB is widely used in system analysis, covering engineering computation and control design. It consists of 2 major components, MATLAB and Simulink. 4. Time domain analysis of control systems using MATLAB. 1. Transient response and performance indices calculation of second-order systems. Using a unit negative feedback system as an example, MATLAB can quickly plot unit step response curves and automatically calculate performance indices. 2. Approximate analysis of transient response in higher-order systems. By applying dominant pole concepts, pole zero cancellation, and neglecting distant poles, a second-order approximate system can be obtained. Comparing the unit step responses of a fourth-order system and its second-order approximation shows that the approximation closely matches the original, simplifying analysis and computation. That concludes this lesson. Thank you for listening. See you next time.